Let me continue my discussion on the electrical phenomena in insulators. As we have discussed last time, these are basically dielectric materials and they are used as capacitors when they are placed, when the materials are placed between two electrodes. We have discussed various aspects, various parameters of the dielectric phenomena, and also discussed different atomistic mechanisms of polarization, because the dielectric constant actually arises from the polarization of the insulators under the influence of the external electric field, and there are very different mechanisms by which this polarization takes place. Basically, polarization means there is a dipole or creation of dipoles or dipole moment. So, it is the increase of the dipole moment that leads to polarization. We have discussed 4 different mechanisms of polarization, namely the electronic polarization, atomic polarization or ionic polarization, orientation polarization, and also space charge polarization. We have also looked at very briefly, there are little sub classification of these 4 types of polarization. 2 of them have been again classified or subdivided into 2 groups each, particularly the orientation polarization. We have a high frequency version as a low frequency version. High frequency version is applied to primarily ferroelectric materials, about which we will discuss later, and low frequency, the dipolar version is primarily applies to glasses. For the space charge polarization also, we have 2 different categories. One is the interfacial space charge at the electrodes, which we have discussed, and just like the electrolyte is an interface, grain bound region, particularly polycrystalline ceramics, is are also plays a part so far as the interfacial polarization is concerned. So, that creates certain boundaries where space charge can accumulate, and therefore, the dielectric polarization can take place. Next thing is, if we have a electric field, not a DC field, but a alternating field, AC field, then there will be a frequency, and the frequency dependence of these kind of mechanisms are not same, because these are, there is some charge transport or charge movement, displacement of charge from one side to the other. So, it needs some time. So, the so called the relaxation time, the frequency at which these changes can take place are different for different mechanisms. One can visualize the electronic polarization, where only the displacement of the electron cloud or the deformation of the electron cloud takes place, and this can take place at a very high frequency or very high speed. So, the relaxation time is very small, and therefore, it can respond to almost any kind of frequency which is applied from outside. Whereas, if you look at the space charge polarization, that is the slowest process in this 4 categories, because it needs slightly longer range of transport of charge species, in this case primarily the ions, the mobile ions. So, that is time consuming, and therefore, the time required for the movement or movement back and forth is much larger, or the relaxation time is larger. So, it can only respond to a very low frequency region. So, if you plot the polarizability, the alpha which has been defined earlier, the polarizability as a function of frequency from a wide range of frequency from almost 1 hertz to about 10 to the 18 hertz. In this frequency range, 4 different mechanisms respond in 4 different ways. The slowest process of course is the space charge. So, it can respond only for a low frequency. So, if you increase the frequency, the space charge will not be able to respond. So, there will be a plateau. So, at this low frequency, all the 4 mechanisms are operative, including the electronic, ionic, dipolar or actually orientation polarization and the space charge polarization. So, if the frequency is very low, all the 4 are operative. So, the dielectric constant as well as the polarization is much larger. Whereas, if once increases the frequency slightly, then there will be plateau, and this plateau actually corresponds to 3 remaining mechanisms. The space charge mechanisms will not be operative anymore. So, the polarizability as well as the dielectric constant and polarization will reduce as a function of frequency, and 3 of them will be operative at this frequency range of around 10 kilohertz or so. Whereas, once again if you increase the frequency to about 10 to the power 10 hertz, is around gigahertz range, then you will find the 2 of them has been disappearing, both the space charge and the dipolar. Ionic and electronic will still be there, because their relaxation time is much shorter, and so they can respond to very high frequencies. Till at higher frequency, more than 10 to the power 14 or so, almost optical frequency region, it is only the electronic polarization or the electronic mechanism will be operative, and other 3 will not be operative. Therefore, the dielectric constant, polarizability, all of them will reduce. So, at very high frequency you have only electronic polarization mechanism operative, and the polarization or polarizability is much smaller. In general, as a increasing frequency, you can see the polarizability as well as the dielectric constant slowly decreases over a wide range of frequency. And you can also see that total alpha at any given frequency is actually the summation of all the 4 polarizabilities: the electronic polarizability, ionic polarizability, orientation polarizability as well as the space charge polarizability. So, these are the summations of 4 different mechanisms which will give rise to the overall polarizability or overall polarization and dielectric constant. So, the dielectric constant actually as a function of frequency will automatically always decrease, because the different mechanisms will be operated at different frequencies. So, that is a common phenomena of any dielectric material. The frequency, as the frequency increases, the dielectric constant will slowly reduce. In association with that, or associated with this phenomena, there is another phenomena also takes place, which is given in this picture. This is also the same picture, also although it has been drawn in a slightly different way. It is not the exact manner in which the other one was drawn, but basically it also represents the same thing. You have a space charge polarization, you have dipolar polarization, and then you have ionic polarization and electronic polarization. In these 2 cases, of course, as in the earlier case also, there is a peak through which it goes. It is not slightly differently than the other 2. Okay. So, it has a resonance peak here, and therefore, they behave slightly differently. even in the polarizability there is a peak, but normally there will be peaks, in the dielectric loss. Of course, this particular quantity or the parameter has not been introduced so far in this lecture. We will try to find out later on what is the dielectric loss, but for the time being let us see whenever there is a transition from one mechanism to the next mechanism, or one mechanism is getting off as if because the frequency is increasing, there is a loss of energy. So, there is a dielectric, what we call a dielectric loss. This basically determines or basically represents a loss of energy at that point. So, all these transitions will be associated with some dielectric loss or a energy loss at the frequencies where the transitions is taking place. So, this is the additional information which is there in this particular picture compared to the previous picture. Okay. So, it gives on the top is the change in the dielectric constant or the polarizability is basically proportional, and the increasing frequency, and the bottom curve represents the dielectric loss. Okay. So, this is a typical frequency dependence of dielectric behavior of different materials. Well, so far basically we are talking about the dielectric material. There is a dielectric constant and there is a polarization as a function of applied electric field, and this there are in fact two varieties of dielectric material. What we are discussing so far is actually called the linear dielectrics. These materials, a group of materials in which the dielectric polarization is linearly related or is proportional to the applied electric field. The dielectric constant is not dependent on the electric field. So, the proportionality is basically the dielectric constant, and therefore, because of this linear relationship, this group of material, a group of material which we will talk later, they are called linear dielectrics because the slope represents the dielectric constant. Okay. So, it is a plot of polarization versus applied electric field, and it becomes a straight line, and the slope is actually the dielectric constant. So, since the dielectric constant is independent of the applied electric field, it is called the linear dielectric. So, the group of materials which depicts this kind of a phenomena, this kind of relationship are known as linear dielectrics. Most of the materials, common materials, ceramic materials like porcelain, silica, alumina or calcium oxide, or most of the insulating oxides, even nitrides, borides, etc., all have a linear dielectrics, except a group of mixed oxides which are known as ferroelectric material, which will be discussed later in the class, next class maybe. So, these are most of these materials are called linear dielectrics, except a group of materials which are called ferroelectric material or piezoelectric material. Those are non-linear characteristics. So, these are, so one can distinguish between the two groups of material depending on the characteristics of variation of dielectric constant as a function of applied field. So, this is the characteristics of linear dielectrics. Two more phenomena is also important. One is the dielectric strength. Now, when we apply electric field against a dielectric material, we say it is polarized, and as a result you have generation of dipole moments and so on, and it stores energy by through a process of polarization. But can we apply any voltage we like? The answer is no. we have a limit of electric field which we can apply for each material. So, the materials are also characterized by the maximum electric field that can be applied on these materials. Beyond that, this material, what we call a breakdown, takes place. So, there is a dielectric breakdown, okay. And that means there is a leakage current, there is a heavy leakage current and the material almost become a conductor. In fact, what happens, there is a avalanche breakdown or a carrier multiplication. That means initially the number of carriers are low when it is actually acting as a insulator or a dielectric material, but if the dielectric the applied voltage crosses the dielectric strength of that particular material, then the chemical bonds between the atoms actually breaks down and the material almost becomes a conductor. So, there is a heavy short circuit and there can be an explosion, because suddenly a very high current will flow through the material because you have applied a very high voltage, and therefore, there can be an explosion and a big spark and so on. So, that is what we call a dielectric breakdown. So, it is very important to know what is the limit of the applied field which can be exposed to. So, dielectric strength and the dielectric breakdown. So, dielectric breakdown is the limiting phenomena when the applied field exceeds the dielectric strength. So, normally it is volt per centimeter or volt per meter, that is how it is expressed. Behavior of dielectrics under alternating field. We have started discussing about it little while ago, but let us look at it little more details about this. The current in an ideal capacitor under an alternating field leads the voltage by 90 degree. From the electrical engineering point of view, one knows that whenever there is a capacitor, the voltage and the current are not in phase with each other. So, current normally leads the voltage by 90 degrees. That is the ideal situation when there is no loss, there is no leakage current, there is no the insulation is almost perfect, or the resistance of the insulating material is infinity. So, if that happens, the current leads the voltage, particularly in case of a alternating field sinusoidal voltage, by 90 degrees. Okay. So, however, since there is a finite resistance always or finite conductance, some very small amount of current goes through it, passes through it. So, there is the current actually does not lead by 90 degrees, but slightly less than 90 degrees, and that angle is known as the delta. So, it is less by an angle delta. Now, the expressions for different parameters under the alternating field are like this, representing the electric field and the displacement, the flux density in complex notations. When we are having a alternating field, then we have to use a complex notations like E equal to E0 exponential I omega t. Omega is the angular frequency, t is the time, and I is the imaginary quantity. And the corresponding displacement, the effect of the electric field or the induced flux density is actually d equal to d0 exponential minus I omega t minus delta. So, this is actually a kind of the effect of voltage, that means the current, the kind of current. Okay. And knowing that d and the E is related by this complex quantity, the dielectric constant and in this case it is k star, it is not k prime which we have used earlier. Now we use a k star because it is now a complex quantity, and therefore D equal to k star into E. So, this we can be further written k star as D by E equal to, we can divide them into two components, one is the real component, another is imaginary component. So, one is k s exponential minus delta I delta, and that is equal to k s cos delta minus I sin delta. So, there are two different components, one is the real component and the imaginary component, and k s in this case is actually the what we call the static dielectric constant. That means a DC field under DC field, whatever the k value of the dielectric constant under DC field, that becomes k s, that is a very low frequency dielectric constant. Okay. So, in which k s also is represented by d 0 by E 0, okay, which we have seen earlier. These E 0 and d 0, these are the two constants, and basically they are the low frequency constant, low frequency values. With the static, or in other words one sometimes called the static dielectric constant. Okay. There is no variation of frequency here. In terms of the complex dielectric constant, then k star equal to k minus k prime minus I k double prime equal to, that is the expression of the complex quantity, complex dielectric constant, and that can be again represented in this manner. Once again we can introduce a permittivity, which is a complex permittivity. So, when the DC field we do not use the complex permittivity, but in AC field the same permittivity becomes a complex quantity with an imaginary term, and then we can write 1 by epsilon, epsilon prime, epsilon naught, epsilon prime minus epsilon double prime, I epsilon double prime. Okay. Sorry, there is a little mistake, epsilon 0 should be subscripts, these should be subscripts, okay, like k s. Well, to continue the same discussion, k prime, the real part of the dielectric constant, can be represented as k s cos delta, and k double prime equal to k s sin delta. Accordingly, you can have a tan delta equal to k double prime by k prime, also equal to k epsilon double prime by epsilon prime. Okay. Now, from these equations one can find out there are two components of the current. One is called the charging current, which is actually out of phase. Charging current is the out of phase with the voltage you apply or the electric field you apply. So, I c is equal to I omega epsilon prime E, E is the applied field, whereas the loss current which is in phase with the applied field equal to omega epsilon double prime E, E is the electric field, which can also be written as sigma E. This is from the kind of Ohm's law, you can electric field and the current. So, this becomes a constant which is equal to sigma. So, we have a sigma or the conductivity, which is called the dielectric conductivity, and it is a product of two parameters. One is the omega, the frequency, and the imaginary part of the dielectric permittivity. This product of these two quantities actually is the sigma, or this is different from DC conductivity. Okay. So, DC conductivity the value will be different, whereas the AC conductivity this sigma is, that is why it is called the dielectric conductivity. Okay. As we have just discussed that there are two components of the current. One is the charging current, which is out of phase or 90 degree ahead of the electric field or the voltage in this case. So, this is a plot of vector diagram for voltage or current against voltage. So, you have both of them are right angle to each other, and this is the charging current, this expression, which is ahead of 90 degree ahead of voltage, and the loss current which is in phase with the voltage. So, if you find out the quantity, ideally it should be 90 degree, but the resultant current is actually along this line, which is at an angle of delta from the current axis. So, this is what we call the loss angle, and this is normally small, and if the loss current is more, if this quantity is more, then this will be more inclined and the delta will increase. So, higher is the loss current, higher will be the delta, and from this also higher is the conductivity, higher will be the delta. So, delta is actually a measure of the loss of energy which is conducted away through the dielectric. Ideally there should not be any conduction, but in reality there is some conduction, and that is measure. The conductivity is the measure of how much loss can take place. Higher is the conductivity, higher will be the current and higher will be the loss. Okay. Now, there are few parameters which characterizes the dielectric materials or the capacitors. These are the four different parameters which characterizes the performance or the quality of the dielectric material or the capacitor made out of the dielectric material. First of all is the loss tangent. This is a characteristics of the material of dielectric material with which a capacitor is made. So, it is independent, it is an intrinsic property, it is an intrinsic property of the material. It is not the intrinsic property of a capacitor, because capacitor contains some geometric factors. So, the capacitance value also includes a geometric factor, but the dielectric constant as well as loss tangent or dielectric loss are the material parameter and the intrinsic property of the material. The way we prepare it, the way we synthesize it, or the particular crystal structure, the chemical composition, and so on and so forth. Okay. Then we have a loss factor. Loss factor, tan delta is just the loss tangent. So, there are different parameters used in the literature. Loss factor is epsilon prime multiplied by tan delta. So, this is not the loss tangent and loss factors are two different quantities. So, the loss tangent is only tan delta, whereas loss factor is tan delta multiplied by the real part of the permittivity. There is another parameter is also used to designate how good a capacitor is, that is what is called a quality factor or sometimes called Q factor. This Q factor is nothing but the inverse of tan delta. So, higher is the loss, lower will be the quality factor. So, that means we will have always try to find out where the loss is lowest. Okay. So, higher is the quality factor, that means the tan delta value is low, and therefore, that is a better material or better capacitor. So, that is quality factor, and finally, which we have already discussed, the dielectric conductivity sigma, that is epsilon double prime multiplied by the electric field E. Okay. So, dielectric conductivity also is a parameter which determines how much is the leakage current, and higher is the leakage current, higher will be the tan delta and lower will be the quality factor. Okay. So, and the loss factor will also be low, will be high. So, these are the 4 parameters based on this angle between the resultant and the current axis. Okay. Now, any capacitor can have a equivalent circuit. Okay. That means capacitor is not an ideal capacitor. So, it has a finite resistance or a finite conductance, and therefore, a real capacitor can be represented in this manner in a what we call a RC circuit. It is a very simple circuit where a ideal capacitor and a resistance is put in parallel. Okay. So, the real capacitor has ideally this resistance should not have been there, it is infinity, but since there is a finite resistance, you have a resistance also have to be put in parallel with the capacitor. So, that is what we know, that is known as the equivalent circuit of a capacitor. Based on these equivalent circuit parameters, if this is C, the capacitance and capacitance of an ideal capacitor, and then this is R, from this parameter, from this equivalent circuit parameters also one can find out the parameters which you have already discussed. Tan delta in this case, the imaginary part of the K and real part of the K, that we have already seen, and in terms of the equivalent circuit parameters, this tan delta can be represented like this: V by R, R is the equivalent circuit resistance, and V omega C, C is the equivalent circuit capacitance, okay, and V is the applied voltage. Okay. So, tan delta is like this: V by R is the imaginary part of the K and real part of the K is V omega C. So, ultimately it is 1 by omega C R, okay. 1 by omega C R in terms of the parameters of the equivalent circuit. Okay. So, the tan delta can also be represented or measured by this expression, provided we know the equivalent circuit parameters. In fact, the reverse is also true. If you find out the tan delta and also the voltage, one can also find out what will be the equivalent circuit parameters C and R values by measuring as a function of frequency, in fact. Now, we have already discussed that one of the major purposes of capacitor or using a dielectric material to construct a capacitor is basically to store electrical energy in the system and use it whenever is needed. Okay. So, the maximum energy that can be stored is actually equal to half C into V square. V is the applied voltage. Okay. This occurs, this stored energy of course is dependent on frequency. It is not the same at all frequencies. So, depending on the frequency, the amount of stored energy will vary, and the maximum energy is stored when the cos 2 omega t equal to minus 1. So, it is a frequency dependent as well. Okay. So, that is also another important aspect one must remember. This we have already seen earlier. The smaller is the R, greater is the energy loss. Smaller R means higher conductance and therefore more leakage current and therefore more energy loss. So, part of the energy is greater part of the energy is lost than what it can be stored. The energy loss takes place due to conduction through the resistance, that is already the same thing which has been repeated here. Now, we have discussed little bit about the frequency dependence. So, when we are discussing about the atomistic mechanisms of dielectric polarization, now we look at it also from a different angle, frequency dependence of dielectric parameters as a whole, not only just the dielectric constant polarization and so on. So, we are not discussing here polarization, we are trying to look at the overall dielectric constant, how it depends on the frequency. For any dielectric material, the permittivity is frequency dependent, for that is because the polarization is frequency dependent. For any particular mechanism of polarization having a relaxation time of tau, we have said earlier that for any process there is a time constant, and that is the relaxation time, that is the characteristics time which it needs for displacements, because the charge is getting displaced from one point to the other. So, there is a time constant and time is necessary for that movement to take place, for that change to take place. So, one may have two nearly constant values of permittivity, what we call epsilon s, or the static dielectric constant or static permittivity, or it is basically a low frequency permittivity and a very high frequency permittivity. Both of them are more or less constant over a period of over a few frequency range, some frequency range. Okay. Now, using these parameters del epsilon s and epsilon infinity, one can write the complex permittivity under an alternating field in this manner. Once again, epsilon star equal to epsilon infinity plus epsilon s and epsilon epsilon s minus epsilon infinity 1 plus I omega t. So, this is the overall expression of the permittivity in terms of two constants, one is epsilon infinity, another is epsilon s, which is low frequency permittivity and the high frequency permittivity. Both of them are constants, but it goes through a transition, right. We will see that in a minute. So, these are a few more equations. This is, we know any complex quantity can be represented in this manner. So, you have a real quantity, real part and the imaginary part with a imaginary quantity, and the earlier equation can be subdivided into these parts, okay, these components. So, here actually we are trying to find out the real part of the permittivity as a function of once again two quantities epsilon infinity and epsilon s. Okay. These are the two constant and they are frequency dependent by this process, and tau is the characteristics temperature, characteristics time constant for this particular process. Similarly, you have epsilon double prime, which is the imaginary part of the permittivity, and once again it is related to these two quantities and constants, and then a frequency omega as well as the tau is the time constant or the relaxation time of that particular process. And just by dividing one by the other, one can get tan delta equal to this kind of a expression. Once again, the three or four parameters which are used here is epsilon s, epsilon infinity, omega and tau. Now, if you plot these parameters, three parameters have been plotted here. One is the dielectric constant, or basically which is proportional. Here it has been plotted k prime, which is proportional to also to epsilon prime, which has been used in the equation previously. So, this is either k prime or one can say epsilon prime. This is actually conductivity or omega into epsilon double prime, and this is loss factor or the loss tangent. The loss factor is actually k double prime or k epsilon prime into tan delta. So, it is basically a loss curve, this is a conductivity curve, and this is the dielectric constant curve. So, in any material, this is a very general characteristics of any material. This is the frequency dependence of the dielectric constant or the dielectric parameters. This is your dielectric constant. So, at lower frequency dielectric constant is large or higher than the higher frequency. So, these two, this is become almost independent of frequency in this region, and here also it is almost independent of frequency. So, this value is known as the static dielectric constant or k at omega equal to 0, and this value is k at omega equal to infinity. So, this is high frequency value and this is low frequency value. So, there is a independent frequency independent region, then there is a transition, and then once again a frequency independent region. So, this is a very general characteristics of any dielectric so far as the frequency dependence is concerned. Thus, the reverse takes place so far as the dielectric conductivity is concerned, or k double prime or epsilon permittivity, real imaginary part of the permittivity. So, it goes through once again a transition at the same frequency, and this frequency characteristic frequency is 1 by tau, that is the inverse, of the relaxation time. So, that is the frequency. So, omega tau is actually equal to 1. So, if you plot as a function of omega tau, this will be 1. So, the inverse of the characteristics relaxation time characteristics time constant, you will get the transition. So, this from higher value to goes to the lower value, in this case it is a lower value to the higher value, and at the same frequency the loss factor or tan delta goes through a peak. Okay. So, this is when the time constant is equal to the frequency, okay, when the time constant is equal to the inverse of the frequency of course, or frequency is the inverse of time constant relaxation time, then there is the whole process is in phase with each with the applied field, and therefore, there is a large loss takes place. So, and the area under this curve actually is the total energy loss. So, higher is the frequency, higher is the conductivity, higher will be the peak, and so on. So, this is ideally in a capacitor we would try to look for where the loss is less, because if the loss is high, not only you are losing a lot of energy, but also because of the current, higher relatively large current, the whole material will get heated up. So, there will be Joule heating. So, therefore, when in practice a dielectric material, we should look for a dielectric material where the loss is low. That is the normal practice. Of course, there are applications. There are applications where dielectric loss we intentionally like to have a higher dielectric loss, because where we need heat. Okay. For example, in a microwave heating actually we need more energy loss from the dielectric, less amount of energy should be stored in the dielectric, whereas more amount of energy will be used up for heating the material. So, if such applications of course, one needs to have a higher loss factor, but most of the other applications will need a low loss factor material. Well, here is a list just to give you some idea the different kind of materials used as a dielectric, as used for capacitors, both in the group of polymers or the plastic, which is a good insulator anyway, and number of ceramic oxides or ceramic materials as such. So, starting with for example, first 4 or 5 of them are actually plastics, different kind of polymers, and these are the different typical values of the dielectric constant. This is the dielectric constant, 2 different frequencies. Of course, as you can see, there is hardly any difference between this this value of the frequency and this value. This is about 60 hertz, whereas the other one is about 1 megahertz, 10 to the power 6 hertz. So, the variation of dielectric constant in this range is almost negligible, very small, you can see, but in general the polymers have a little lower dielectric constant than the ceramics. Okay. For example, fused silica of course is a low dielectric constant, but soda lime silica glass has a higher dielectric constant compared to the polymers, which is more or less in the range of 2 to 4, whereas these are about above 7. And aluminum oxide, as you can see, there is slight variation here in the aluminum oxide even in this range. That means, this is 6.5 lower than the low frequency value 9. These 3 ceramic oxides are very special. Okay. As you can see, titanium oxide or titanium dioxide, mica. Mica is a natural mineral, it is not a synthesized mineral, just natural flakes of mica can be used, in fact has been used very extensively for over a long time for making capacitors. And then the last one is barium titanate, it is a synthesized material, it is a mixed oxide of barium oxide and titanium dioxide, and by heating them at a higher temperature one can make a compound having different crystal structures compared other than that of barium oxide or titanium dioxide, and one can have a dielectric constant of the very high order, about 2000 to 5000, and in some cases it can be more than this value also. Okay. We will discuss barium titanate in greater details at a later stage, but compared to most of the other dielectric material, the dielectric constant of these kind of ceramics, even titanium dioxide, is around 100, whereas these are in the order of thousands. So, that is a very attractive feature of this particular dielectric material, which incidentally is a ceramic material. Dielectric strength here is more or less same, except in some variations, but you can see these are almost 10 to the power 6 volts per meter, which is of the very high order, 20 megavolts per meter. Here of course, the polymer have a relatively high breakdown strength or dielectric strength compared to those of ceramics. Ceramics except mica has a very high value of 40, but other ceramics are relatively low. Okay. But even then they are quite high. Tan delta, the values of tan delta are of this order for all materials, as you can see it is 10 to the minus 3 or 10 to the minus 4 like that, and tan delta for barium titanate or TiO2 is slightly high, aluminum oxide is about little higher than the others, but mostly it is measured as 1 megahertz and the values are like this. Resistivity, it is obvious that all of them are very high resistance, but it varies to some extent, but most of them tend to higher than 10 to the power 10 ohm centimeter. So, these are the different in fact they are important dielectric materials used in industry for different purposes. I discussed two important devices which are very commonly used, made of ceramic capacitors or ceramic dielectric material. One is a capacitor. We have discussed that device on and off during our discussion. This is nothing but an electronic device constructed from alternating layers of a dielectric and a conductor. So, there are a dielectric is sandwiched between two conductors, basically that is a capacitor that is capable of storing charge. So, one of the major purposes of capacitor is to store electrical charge for certain circuits or certain purposes. These can be single layer or multi-layer devices. Barium titanate based ceramic compositions and silver palladium alloy are normally used as the dielectrics and the interlayer electrode respectively. This is for the multi-layer capacitors. Of course, the capacitors which so far we have discussed is basically a single layer, that means single layer of insulator and two layers of electrodes, metal electrodes, right. Now, it is possible to make or design multi-layer ceramic capacitors in order to miniaturize the capacitance effect. That means, in order to miniaturize the size of the capacitance. So, within a small volume one can store much larger quantity of charge. So, that is the purpose of multi-layering. I will give you some example how it is exactly done. It is actually what we call the multi-layer ceramic capacitors or MLCC, and it has been compared with a single layer capacitance like this. So, this is basically a single layer capacitor or sometimes called disc capacitors. This is nothing but a small ceramic disc, maybe a millimeter thick, and then on two sides, on two surfaces, circular surfaces, you have electrodes. These electrodes are basically painted some by a thick film technology, metal pastes are available, and that can be pasted on these painted on the surfaces, and that will make a few micron thick conductor, and that is again soldered between the two leads. So, these are the two copper wire leads, so which can be soldered on the surface of the ceramic disc on which a ceramic metal pastes have been added. So, this is your ceramic disc, then you have a metal electrode in the form of a metal paste, and then you have epoxy, which is basically a potting material, that means it just gets insulated or protects it from the other environments and the surroundings. So, that is a very simple design of a capacitor. So, everything depends of course on the characteristics of this ceramic material. However, if you want to have a volume efficiency of the ceramic capacitors, because capacitors are needed in very large numbers in electronic circuits, by using semiconductor devices like silicon chips, the whole system has been miniaturized to a very great extent. So, to compare or to make it compatible with that kind of miniaturization, capacitors are also needed to be miniaturized, and this is one way of miniaturization. This miniaturization, nothing but you have multiple layers. These white areas are actually ceramic disc, ceramic layers, and the blue ones are the electrodes. So, you have number of layers and number of electrode layers also. So, these layers in fact are very thin layers, unlike the disc capacitors which may be a millimeter thick. These are only about 20 to 25 microns thick. So, by reducing the thickness, actually one increases the overall capacitance, because capacitance is proportional to A by D, that is the area by thickness. So, lower is the thickness, higher is the capacitance. So, by just by reducing the thickness of the dielectric medium, one can enhance the capacitance effect and also use much smaller quantity of the material. Right. Then you have another multiplier effect by a large number of layers which has been added parallelly. As you can see, the alternate layers of the electrodes are extending, not extending to the end. So, this is here not extending to the other end, and the other one is not extending to the on the left end. So, actually these layers, and then of course these are connected on this side and this is also connected on this side. So, these each individual layers are actually electrically they are parallelly connected. Okay. If you look at properly, you will find they are parallelly connected. So, there is an additive effect. Whenever capacitance are added in a parallel, there is an additive effect. So, each of these capacitances are added parallelly, and therefore, within the same volume you have a much larger capacitance compared to this kind of a design. So, compared to these capacitors, these are much more miniaturized, and one can use it much more efficiently. So, this is what we call the metal terminal, which is connecting all the metal electrodes in between. Okay. So, the alternate electrodes are connected on this side as well as on this side. So, this is the basic function of or basic design of a multilayer ceramic capacitors, and the capacitors can be enhanced by this factor. A is the area, N is the number of layers, -1, and D is the thickness. So, lower is the thickness and higher is the N value, the capacitance value increases for the same dielectric constant, because the material constant is not increasing here, not changing, it is only the design which is enhancing the capacitance value. Thickness of each layer is about 20 to 25 micron. And the last one, another very important application of particularly barium the linear dielectrics is here used as a memory chips, that is dynamic random access memory or DRAM, which is quite common in computer technology, based on a memory chip of computers, and these are computer memory chips and several electronic instruments. They use normally, because they are deposited or they are fabricated on silicon chips. So, it is a silicon bearing compounds are better suited for this kind of a dielectric. So, silicon nitride and silicon dioxide dielectrics are normally used, but in this case it is in the thin film configuration, not even thick film, okay, not even micron, a fraction of a micron, and deposited directly on silicon and polysilicon chips, required to be charged and discharged more than 1000 times per second. So, since the dielectric layer is very thin, fraction of a micron, the voltage, the breakdown voltage is very important here. So, you have to understand what is the breakdown voltage exactly of these materials, so that there is no puncture, there is no short circuiting while it is used. So, the random access memory actually works on a charging discharging characteristics of a very thin film dielectric or thin film capacitors. So, charged state is 0 state or 1 state, or and the discharge state is the 0 state. That is how all the memory chips are fabricated, and of course, the more recent advancement is in the area of changing the dielectric from silicon nitride or silicon oxide to barium titanate or barium strontium titanate based compounds. They are called FERAM or ferroelectric random access memory. So, these are the few applications, very few in numbers. Of course, there are many different other applications, maybe we will take up in the next class when we will discuss about the ferroelectric and piezoelectric materials. So, we conclude here by saying that the ceramic dielectrics have become a very important aspect of electronics industry, primarily for their dielectric property and the kind of chip designs or kind of capacitor designs which has been used over the last several decades. Thank you.